Drop a solid iron nail into a glass of water and it sinks immediately. It's exactly what you'd expect. Yet, look at the ocean and you'll see colossal cruise ships forged from thousands of tons of that same iron gliding across the surface. To understand why one small piece of iron plummets while a mountain of it floats, we can't rely on our intuition. We have to look at how the universe calculates reality through exact measurement. This chart outlines the 7 fundamental SI units, metrics like length in meters, mass in kilograms, and time in seconds. Think of these as the unbreakable baseline of physics. None of these 7 quantities can be broken down into anything simpler. But when you combine these base measurements, you get what physicists call derived quantities. By dividing distance by time, for instance, we can calculate speed. The physical world isn't governed by magic. It operates on a strict matrix of these fundamental measurements, all combining to dictate exactly how matter behaves. Take length, for example. If you measure an object's length, breadth, and height and multiply them together, you get its volume. That is simply the exact amount of physical, three-dimensional space that an object occupies. For liquids, measuring that space requires a laboratory tool called a graduated cylinder, which captures the fluid in a glass container with fixed capacity markings. If you look closely at this diagram, you'll see the fluid's surface isn't actually flat. Water grips the glass to form a downward curve called a concave meniscus. Pour mercury in, and it does the exact opposite, bulging upward into a convex meniscus. To find the true volume of water, you must align your eye level perfectly with the lowest point of that concave curve. Reading it from a higher or lower angle creates a parallax error, giving you a falsely skewed number. That works perfectly for fluids and regular shapes. But standard geometric math formulas fail completely when you need the volume of an irregular solid, like a jagged stone. Watch what happens in this measuring cylinder when a stone goes in. By taking the starting volume of the liquid and subtracting it from the new, higher volume, the numerical difference gives you the exact capacity of the stone itself. Even when a shape defies simple geometry, we can translate its physical space into exact volume simply by observing how it pushes other matter out of the way. Looking at this balance scale, we see the traditional tools used to measure mass. When you take a substance's mass and divide it by its volume, you discover its density, a measurement of how tightly its matter is packed together. This animated triangle represents the relationship between density, mass, and volume. It's a mathematical shortcut to calculate any missing variable. Cover density with your finger, and you're left with mass positioned over volume. This instantly reveals density equals mass divided by volume. Now we can finally solve our Act 1 puzzle. That solid iron nail sinks because its strict density is greater than the density of the water it displaces. The ship floats because its hull is designed with vast hollow spaces filled with air. This increases the total volume, dropping the overall average density of the vessel below that of the water. Looking at this conversion sequence, we can scale density down from massive to microscopic. Because there are 1,000,000 cubic centimeters in a cubic meter and 1,000 grams in a kilogram, 1,000 kilograms packed into a cubic meter perfectly equals just 1 gram packed into a single cubic centimeter. Density reveals that buoyancy isn't decided by how heavy an object is. It is entirely determined by how efficiently that mass is distributed across physical space. Once we understand physical mass, we can measure motion. By taking the exact distance an object travels and dividing it by the time it took, we derive speed. In this photo, we see a horse racing on a track. If that horse travels 80 kilometers in 2 hours and a camel travels 120 kilometers in 6 hours, you have to do a little math to prove which is actually moving faster. The only way to objectively compare them is to break those trips down into a single unit time, like 1 hour, that hourly speed down to seconds. To convert kilometers per hour into meters per second, you divide 1,000 meters by 3,600 seconds. That fraction simplifies to exactly 5/18, which you can multiply against any hourly speed. To go the other way, converting meters per second back to kilometers per hour, the fraction flips. You multiply your speed by 18/5, giving you exactly 3.6. Speed provides us a standardized mathematical language. It allows us to objectively compare the motion of any two objects in the universe, regardless of the total distance they ultimately travel. Mastering a handful of fundamental units makes it possible to measure almost anything. We can calculate the total fluid volume of the Earth's oceans or quantify the mass of heavy metals like osmium, the densest known substance on the planet. This photo captures Usain Bolt stopping the clock at 9.58 seconds. This same exact framework of measurement scales directly to human limits, allowing us to precisely verify world record athletic speed. From a heavy iron nail dropping into a glass of water to an Olympic sprinter crossing the finish line, the physical universe is bound together by a single, interconnected mathematical framework of measurement. But there are abstract things out there we haven't quite figured out how to measure yet. If you could invent a brand new unit of measurement for something intangible, what would it be? Let us know in the comments below.